Software Engineering Radio Episode 2, Dependencies. Welcome to this episode of Software Engineering Radio. In this episode, Markus and Eberhard talk about managing dependencies. Dependencies are a very important topic in software engineering, and it's not easy in big projects to handle them correctly. So before we go into detail on this topic, I think we should discuss the prerequisites. What do we expect the listener to know about object orientation? So I think I'll just mention a couple of topics. So we don't want to provide an introduction to object orientation. So we assume that you, the listener, knows what classes are, what objects are, all these kinds of things. You know that there are interfaces that you can let classes implement. There is this concept of polymorphism. So if you invoke an operation on an object, then depending on the dynamic subtype of the declared class, the respective method is invoked, and also objects can have relationships. So if you look at a UML diagram, you can draw those association lines between classes, which means that at runtime, objects, instances of those classes, know each other and can talk to each other. And this podcast episode is actually about the relationships, the associations between those objects, between objects in general.
In terms of dependencies, so it's not really focused on inheritance, for example, and that's one of the already quite interesting points, because usually object orientation is really, a lot of people think it's about inheritance because that gives us reusability and so on. And if you do object-oriented systems for some time, you realize that in fact that's not the case. It's not inheritance that is so important, but it's rather delegation, calling methods on other objects, using other objects as a service provider for your own object, and wiring things together. So that's probably one of the interesting points, and it's in a way confusing that inheritance has become this first-class citizen that is available in all of the object-oriented languages, while there is no real concept in terms of delegates in.
Right, this is interesting to see, because in the last episode we talked about patterns, and the design patterns book, the Gov book we talked about, actually uses a lot of delegation. So instead of using this built-in feature of inheritance, many of the patterns use delegation in a creative way to achieve flexibility that would not be possible by just using inheritance.
Strategy, for example.
Right. So also, if you look at the UML language, you can represent a relationship between classes as a first-class construct, right? You have a line between classes. So an association between objects is not implemented as an attribute that happens to have the type of the other end. It's really a first-class concept. And in programming languages, there isn't this concept. You can only add an attribute of the other type, but you can't have associations explicitly.
And the most important part is that object orientation is really about deconstructing a system into smaller blocks and then wiring all things together. And this can only be done using dependencies and not using inheritance, of course.
Right. Also, a final word on that. Inheritance is always static. You have to statically define in your source code the class from which you inherit. If you use delegation and associations between objects, you can change a lot of these things at runtime. So you're much more flexible.
Yeah. Even though I'm not sure whether this is the case for all object-oriented languages, but that's probably a different topic.
Yes.
So the question is why this is so important. And I think one of the main points why this is so important is because of testability. Because only if you have a flexible system and you can have a reduced set of objects wired together and test them in isolation, you have a really easily testable system, because otherwise you can just get the whole thing and test it as a whole, and that's not a practical approach. And I think, especially concerning the quality of software and productivity and so on, it's really testability that is the thing that is so important to keep in mind if you talk about dependencies and so on.
So if you generalize that a little bit, it's basically about modularizing a system. So you want to be able to extract some parts of a system and replace them with some other mock or stub, so you can easily write or implement test scenarios. If you are not able to manage your dependencies reasonably, then if you pull on one class, then basically you pull and pull and pull, and you have the whole system in your hand. You don't want that. You want to be able to extract certain parts of the system, isolate them, provide an environment in which they feel at home, so all their dependencies are satisfied, and then you want to be able to test this part of the system in isolation from all the rest.
Which is the same thing. I mean, that's what I want to stress. It's not about flexibility as a goal in itself. It's rather something that has the goal of testability. That's the main reason. It's also not so much about reusability. It's mainly because of testability, and that's why it's probably so important.
Okay, and another reason might not be the most important one, but again, you might want to be able to, assuming your dependencies are dependencies on some infrastructure things, like for example, if you implement enterprise Java beans, and inside your bean you have, or inside your business logic you have dependencies on various J2EE artifacts, such as a JNDI naming directory or something like that, then you want to be able to control the dependencies to those technology specific things in order to, again, be able to remove those technology specific things in order to have a more testable and more flexible system.
Yeah, but again, the main reason, in my opinion, is testability.
Right.
It's not so much that you want to port the system later on to a different environment that is not Java EE. Right. Because that is rather seldom the case, and it's also hard to really get the system to the point where this is easily doable. So it's rather about having the flexibility to use a reduced infrastructure, probably not an application server, to do tests.
Now, I think we kind of motivated what the problem is, and also we explained that languages, object-oriented languages, don't easily help us there because there is no way to natively represent associations and dependencies. So what are the classical means of solving that problem? How are dependencies managed in typical object-oriented systems?
I believe one of the ways to do it, or one of the usual ways, is more or less the factory pattern. So it's about having one central part of the system, class or whatever, that is responsible for providing the individual objects that other objects can depend on and satisfy those dependencies.
So what does that mean? So you have a piece of application logic. Like, for example, assume we have a component that calculates some insurance policies, and then it needs to have some, I don't know, mathematical helper component. So it would go in the implementation code, you would go to the factory and say factory.get mathematical helper component, and then you would invoke operations on that one, right? Yeah,
that's basically the idea, I guess.
Okay.
And I think that there are other patterns that are closely related to that. So, for example, there is singleton, which is basically says that there should be one instance of the object available in the system. But that's also a special case of the factory, because it just says that you have one instance. So every time you call the factory, you get the very same instance. So it's not, I mean, it's from the point of view of resolving dependencies, it's not really different. And I think the same is also true for naming systems, because it's also about one piece of the system that produces objects according to a certain given name. So it's ultimately, it's again a factory. So I think it really boils down to that most of the approaches are really factory based, I think.
A naming system is basically a factory where one party of the system can register certain objects under a given name, and another part of the system can then look up those objects using the name. So the various parts of the system have to agree on a name, and then the naming service or naming system or registry can be used to look them up. So it's basically a factory whose contents are dynamically populated by another part of the system.
Yeah, exactly. And I believe the point is it's from the distributed systems environment. So in a way, the distributed naming system, DNS, that you use in the internet is also in a way a factory, but I think the term naming system is rather from distributed systems.
Right.
And in the field of distributed systems, there are other concepts like trader, for example,
Right.
where you specify certain product in terms of attributes. It has to have the usual Hello World example is a printer, so you can say, okay, so you want this many pages and so on, and you get a printer somewhere in the net that provides this level of service. So I think that's why there are two different names is really because the background is different. And in one case, it's about distributed systems, and in the other case, in the case of the factory, it's about usual object-oriented systems, and those intermix, for example, in EGB, Corba, or Java EE environments. So that's why there are two.
So what's the problem? Why isn't the factory a good thing? Why not just use factories and be happy?
The metaphor that you could use is a spider in the web. So the factory is in the middle of this dependency graph. Everybody knows the factory. So if you start to drag one object, one class from this dependency graph, the next thing you get is the factory, and after that you could basically get everything. So it means that you have to reuse parts of the systems or interchange parts of the system can get quite hard because everybody really depends on the factory. The benefit, of course, is that you have the central part of the system where you could, for example, exchange the implementation for a mock implementation.
Can I give a different view? I mean, I agree that factories are usually a problem, but I would argue from a different perspective. So the problem is that if you have a factory that, I don't know, hosts 10 different objects, provides access to 10 different objects. Now, you cannot tell whether a certain module, which module uses which of those objects. So the problem is if using a factory is something you have to do procedurally. So in your implementation code, somewhere deep down in your algorithms, you can say factory.get something. You can even do this dynamically. You can use reflection and all kinds of fancy things to come up with what you want to get from the factory. As a consequence, you cannot see, if you look at the piece of code, specifically at its signature, you cannot see what dependencies it has. Compare this to providing features. If you have a class, and this class provides certain operations, then you can define an interface that declares those operations, and your class implements that interface. And now you can use, for example, an instance of test in all object-oriented languages that can check whether this class provides the respective operations by just checking, if class instance of this or that interface, then you know that it provides those methods. There is no such thing for the other way around. You can't use any reflection or any other features to find out that a class requires a certain other class at runtime to do its work if you use the factory, because the factory provides all kinds of things, and what specifically a class needs is hidden in the implementation code. So there is no way of using reflection or other rather simple tools to find out what dependencies a class has. You have to kind of understand the application logic in order to find out what it talks to, what it queries from the factory, and that's a problem.
And again, UML is kind of advanced on this topic because in component diagrams you can easily say, okay, so this component offers those interfaces and uses these interfaces, and that's it. What is quite hard to do in object-oriented languages, or the usual object-oriented languages at least.
So if we kind of try to come up with a criteria for an approach that doesn't have these problems, what kind of criteria would this approach or would this solution have to fulfill? So for one, it has to explicitly declare which resources it needs. So if class A wants to talk to objects of class B and C at runtime, then it has to be clearly declared that A requires B and C. So you need to have a way of marking this explicitly. And then, of course, you have to have a way how your application code can access those objects. So it's not enough to just declare what you need. You also have to make sure that at runtime, when the program runs, you actually have a way to access what you need. So if a module or a class declares the resources it needs, then there must be somebody who provides those resources to the class at runtime. So if you have a class A and B and C again, and A requires B and C, then at runtime you need some magic that supplies instances of B and C to the instance of A. Another important thing, if a class declares it requires B and C, then it must not be able to access other resources. Because if we explicitly declare which resources we need in a class, then we must make sure that there is no other way of accessing stuff that we did not explicitly declare. So this is, in my view, the criteria a solution has to fulfill in order to be better than what we talked about before.
Would it make sense to elaborate on the topic whether we are talking about classes now or components and what the difference is? Because as I already pointed out, at least in the UML diagrams, this is closely related to components, and also this kind of explicit dependencies is part of a definition of component.
Okay, yeah. So probably makes sense to distinguish these kinds of things. However, one could say that a class that explicitly declares the resources it needs can be called a component.
Okay. The discussion concerning components to me is quite interesting, because usually components are kind of associated with a heavyweight approach such as EGB. In my opinion, the distinction between classes and components is not so clear-cut. And I believe one thing that is quite important in this field and is a topic for at least some years now is dependency injection, because this is one of the rather new approaches and really a basic approach of providing those dependencies. And it's also rather easy. The idea is that you have an external entity that takes all those objects and provides them with the other objects it depends on. So that's quite a simple idea. Basically, it just says that you get an instance of the object, you try to discover which other objects are needed by this object, and then you try to satisfy those dependencies.
So, and how do you do this? How does the object declare which resources it needs?
In a way, it depends on the implementation. So there are different ways of doing this. For example, one of the ways is to just declare some constructor parameters, or you could have setter methods or attributes that can be set accordingly to certain other objects. The nice thing about this is that the explicit declaration of dependencies that we were discussing is done in terms of the programming language, and it's also quite nicely fits into the general concept, because usually those concepts like constructors and parameters to constructors and some attributes that you can set are usual object-oriented concepts. So it's nothing new that has to be added to actually get this.
But what you do need is you need some external, let's call it container, dependency injection container that instantiates the objects, that supplies resources to those objects using the setter operations or the constructor parameters, right?
Yeah.
How do you configure the container so that the container knows which objects to instantiate and what? I mean, okay, now so class declares which resources it needs, but how? And then you instantiate this class using the container. How do you tell the container which object, not just which class, which object it has to supply to those resource setters?
Actually, that also depends, because in some environments, like Pico container, for example, this is done automatically. So you just say, okay, so these are my constructor parameters, and if you happen to find anything that is type compatible with those constructor parameters, then there you go, just set it and pass it to my constructor.
So it looks in all the objects it has, and if there is an object of the type that the other one requires, it passes that one in.
Yeah.
And if there are... Yeah?
But, I mean, that's the auto-wiring approach. Other dependency injection environments like Spring, for example, also provide other means where you explicitly declare which objects should be set to which attributes or properties and so on. So there is a great variety of possibilities there.
So if we look at the flexibility you get from that, there are 3 levels of flexibility with regards to resources in general. The first level is you don't even know the interface of the resource you're talking to. The second level is you do know the interface, but you don't know its implementation. And the third level of flexibility is you know its interface, you know the implementation, but there might be several runtime objects, instances of that implementation of that class, and you can configure which of them you want to provide as a resource to a certain class. And the approach of dependency injection we discussed before allows us to use to wire which instance you want. It also allows you to hide certain different implementations behind the same interface. So it allows you this second and the third kind or way of flexibility, right?
Yeah, that's true.
Okay, so you already mentioned pickle container. What kind of, is this a common technology those days? Is it used in many environments, or?
I'm a little bit biased. So in my opinion, and also what I heard from other people is that Spring is actually the dependency injection container that is largely used. And I think one of the nice things about Spring is that you can use all these different techniques. So you can have constructed dependency injection, you can have dependency injection that is based on set methods, you can have auto-wiring by type, you can have auto-wiring by giving certain names to the components and so on. And therefore I believe it's quite a good approach. And there are other things integrated into Spring as well that makes it quite a valuable piece of code. So that's what I think. But as I said, I'm biased.
Biased because you're a big Spring believer.
Yeah, and I'm working on a book about it and so on. So that's
okay. Okay, so if we evaluate this dependency injection strategy with regards to the criteria we came up with before, so how does that compare? So the setter operations, like if there is class A that requires an instance of class B at runtime, then A would have an operation set B and then as the parameter B, right? So there would be a setter for an object of type B. So this declares explicitly which resources you need. You can use reflection to find out about them. You have a means to access those resources because the container just calls the setter operation, and inside the setter you typically store the object you just got passed in a member variable, and you can use that one later. Also, of course, you have this external entity, which would be the dependency injection container that knows about all the instances and passes in the resources to the respective objects. And finally, you can't access any other resources from your implementation code because if you don't have a setter, you have no way of getting access to those objects. And if you have a setter, you implicitly declare that you have an additional resource. So this kind of fulfills our criteria.
Yeah, and the fun thing about it is that it's basically still the same thing. So there is still this all-knowing factory out there that knows all the objects and so on. Mm-hmm. But in terms of dependencies at the code level, the factory totally disappears. So that's kind of the paradox.
So it's not buried in the implementation logic. It's explicit in the signature.
Yeah, exactly.
And so how do you do testing with this approach? How does this simplify testing in practice?
That's actually one of my more or less favorite topics, because I believe that it's actually the big value proposition for using dependency injection containers. So first of all, you need to define what you mean with the term testing. The first thing that you get is you can do real unit tests, meaning that you just test the class itself in isolation, because everything else can be set into it. So that's one of the things. The other thing that you get is you can easily change parts of the system And if, for example, you could say, okay, so I'm going to use a different database, or I'm not going to use an application server, or a certain subsystem will be replaced by a reduced functionality for this test, and then you put all these things together in a test environment and test that. That's not strictly, it's not a unit test anymore because you don't test a class in isolation, but it's rather kind of an integration test of at least certain classes.
Yeah. That's philosophical anyway, whether unit tests are only allowed to test one single class. I mean, nobody does that in practice, right?
It depends. I mean, the point is that certain functionalities, it doesn't make sense to do unit tests. But the interesting part is that it's not just about having this class and test it into isolation. It's rather that you have this flexibility of also interchanging certain subsystems and so on. So it really helps on a lot of different levels. It doesn't only help on the unit test level, but rather during the whole test cycle.
Now, all this dependency injection sounds really great. However, I think there are some critics say that there is the problem with magic. So you just declare certain setters and then you start your dependency injection container, and then by magic and by some strange means of definition and declaration and auto wiring and all these kinds of things, you get a system that's somehow assembled together. Do you think that's a problem in practice? Did you experience that problem?
It's probably something that you don't feel comfortable with, at least at the beginning. But on the other hand, I ultimately think that a lot about computer science and software development is about giving up control. So, for example, I mean, we clearly do have less control about what's actually happening in the system due to object orientation and polymorphism and method call resolution that is done at runtime and virtual machine and so on. So I can relate to that, but on the other hand, I think it's not really such a big problem in practice. The other thing that you have to take into account is, or that you have to think about is how do you modularize your configuration? And the other thing is there is that's again going back to components and classes. It's quite fine-grained what we are talking about. It's on the class level. So I believe in a way you have to think about more coarse-grained approaches. So at least to come up with modules in your system that are wired together, that you can replace, that have their own configuration files and so on. And that's something that you have to come up with yourself. It's not something that the dependency injection system gives you.
That's actually a good point. This brings me to the question of, I mean, we're basically talking about the class level. This is a very, as you said, a fine-grained level. If we look at more higher levels, like for example the dependencies between layers, like you're only allowed to access model functionality from the GUI layer, not the other way around, then this dependency management thing goes up one level, and it's not about classes anymore necessarily. It might be about package dependencies or on other levels of granularity, and we didn't talk about that. That's maybe a different episode. To illustrate that dependency injection is not necessarily the only approach that satisfies the criteria we presented before, I just wanted to briefly give another thing. So the problem with the factory and the naming systems is that they're typically global. That means that all objects are in there. That means everybody in their implementation code can access all the objects that are in the factory. So if we had a specific factory for each class which contained only those objects that are kind of legal for that class to access, then we wouldn't have the problem, right? So if we find a way of coming up with specifically configured classes, specifically configured factories for each class, then that would solve the same problem. And one way to do this is if you work in the context of model-driven systems, if you use a model-driven software development approach, then what you can do is you can specify your dependencies in the model, like for example in a UML diagram using UML dependencies or associations. And then if you generate a class X from that, you can also generate an object called X factory. And this X factory contains accessor methods for only those resources for which you declared dependencies in the model by using UML dependencies or associations. So then you still access the factory from the implementation code. The access to your factory object, like factory.get such and such, is kind of still buried in the implementation code. But the big advantage is you can only access those things for which you have declared dependencies explicitly in the model. Because if you didn't declare them, the generated factory wouldn't include those objects, and therefore you can't access them. So the problem is not necessarily the fact that you access the factory from implementation code, it's that it contains all objects of the system and you never know which objects you look up from your implementation code. Using this specifically generated factory, this problem can also be solved. So this is another approach.
Yeah, but I mean, the question to me would be, using a model-driven approach, you could also use a dependency injection infrastructure as the basis. So the question to me would be whether, if you compare those two approaches, having a specific factory for each whatever class and using dependency injection, what the benefit is if you use this factory approach. I mean, it's
nothing. I just wanted to illustrate that the problem is not inherently with the factory, but with the fact that it's usually a global thing where everything is registered and everybody can access everything. And you satisfy those requirements we outlined before, either through dependency injection or through other means, if you have ways of tweaking it so that it actually works. And I mean, writing factories for each class manually is not something you'd like to do, but if you generate stuff anyway, then this is an approach. What do you do if you can't use dependency injection or some of the other magic we just talked about? Are there other means of kind of trying to get your dependencies under control?
Actually, I can't think of any cases where you can't use dependency injection. So, I mean, if you have an existing system that uses a factory-based approach and is quite large, then introducing a dependency injection is probably not the way to go, because it's just so much effort that you have to spend. But I think it's hard to come up with cases where you can't really use dependency injection. But that's probably a different thing.
I mean, there are other things to kind of come to grips with your dependencies. For example, you can use tools like dependency software tomograph, for example, which allows you to visualize dependencies. There is another tool on SourceForge which is called DepFind for Dependency Finder, which allows you to do the same thing. So it kind of doesn't control your dependencies, but it helps you see them. Other things is, for example, you can use aspect-J to kind of log the dependencies you have, or even you could write static compile time aspects that output an error message if you access code or resources which you kind of shouldn't. Like if you have a UI layer and a model layer, and the model layer accesses the UI layer, which is not allowed, then you can write a compile time aspect that says whenever a class in that package accesses code from another package, then output an error message.
Yeah, and there are other tools. I mean, we could also mention SonarJ or the Matrix plugin for Eclipse. Right. They basically do the same thing. And actually, that's probably one of the drawbacks of dependency injection. If you heavily rely on things like auto-wiring and so on, there is a certain lack of tools. So, for example, in the Spring world, I don't know of any tools. I mean, I'm not sure whether... I'm pretty sure that there isn't any tool that provides you with a graph of the dependencies in the system if you rely on auto-wiring.
So dependency injection is not a magic bullet, it's not a silver bullet, but it helps quite a bit.
Yeah, sure.
It's interesting to see that mainstream infrastructures such as, for example, Enterprise Java Beans also adopt this approach now in EJB3. Dependency injection is the way to connect components, right?
As I said, I'm biased. So a colleague of mine did an evaluation of the Adventure Builder, because that was now ported to Java EE.
What's the Adventure Builder?
That's one of those example applications that used to be Pet Store, and now it's called Adventure Builder. So it was done on J2EE 1.4, and it's now ported to Java EE 5. And the fun thing about it is, or probably the sad thing about it is, that you end up with code that still relies on JNDI instead of a naming system, instead of using dependency injection.
But I thought EJB3 uses dependency injection.
Yeah, that's exactly the problem. The problem is EJB uses dependency injection. So as soon as you have a different class, a normal class,
like or servlets or all these kinds of things.
Also, those Java E class. I mean, as far as I know, everything. As I said, it's something that one of my colleagues did. As far as I know, also the other Java E artifacts like servlets and so on can be dependency injected. But if you do a simple util class that has to have access to the data source, that is
right, a non-managed class.
Yeah, then you end up using JNDI to look it up.
Or you can pass it in as a parameter.
Yeah, but I mean, either way, it's not probably what you want to do. And the other thing is that in Java E5, you declare those dependencies using annotations.
Right.
And in my opinion, the approach of using just normal interface, normal class, normal methods or constructor parameters is better. But I mean, but that's just my opinion.
Although, of course, using annotations, you can specify more criteria, right? For example, instead of just saying, there is a setter that expects an object of type such and such, you can use an annotation that says, I need not just any object, but an object with these and those properties. So that does have its benefits.
But the drawback, in my opinion, is that you statically at compile time depend on the infrastructure. Right. And that's probably, I mean, it's so you end up having your business code depend on annotations from EJB, and I mean that's probably not what you want.
Right, and also if you use annotations to specify the specific criteria that should be used for finding the resource, then that's probably not a good thing, because typically you don't want to specify those criteria when you code, but rather later when you deploy. And when you deploy, you have no way of changing, the stuff you wrote down as annotations.
Yeah. So.
Okay,
I mean, there are ways to do that in Java E5 as far as I know.
So you can override the annotations through external specifications.
Yeah, JNDI and so on. So I mean, the point to me is I don't see Java E being superior to approaches like Spring, for example.
Oh, you're biased, right?
yeah, that's true. But I mean, we'll see about that. I'm looking forward to get more experiences with real-world systems and success stories about Java E5 projects and so on.
Right.
It's going to be interesting.
Okay, so I think before we finally wrap up this episode, I think it's worth mentioning that, of course, if you found out that you have too many complicated crisscrossing dependencies, then it's a good thing of redistributing responsibilities between classes or other building blocks so that the number of dependencies actually is reduced. However, and that's the point about which we discussed today, you first have to find out what those dependencies are. And if they're hidden in implementation code, it's a very hard thing to do. And that's where dependency injection and the other things we talked about can really help to kind of make dependencies obvious.
Yeah.
Okay, anything else you want to say?
Yeah, I just want to stress again the point of that
Spring.
that you need a more coarse-grained layer. That's probably the other thing that you have to take into to think about, because most of the time we were talking about dependencies among objects, and there is this other layer that is quite important as well. And dependency injection is clearly no solution for that, I think, or at least you have to think about how to make it a solution for these things. And that's probably also where model-driven approaches fit into the picture.
So it seems like this is a good point where we could hint on some potential future episode where we could discuss those architectural dependency management issues.
Yeah.
Okay, so that's it for today.
Okay, great.
This was another episode of Software Engineering Radio. For general information, feedback and past episodes, go to se-radio.net. Software Engineering Radio wants to thank Henning Pauli for providing the music we use on this show.